Hello, this is Jemison with PolyTutor. Today we're going to be looking at induction proofs for the 2026 Mathematics Extension 1 syllabus. So the first thing we're going to get into is the structure for an induction proof. An induction proof is a three-step process by which you try to prove or disprove sort of like recursive sequences or like two related mathematical objects. So you could, for example, prove by induction some sort of arithmetic sequence. You could also do geometric sequences, you could do factorials, and you could also do divisibility. These are the four types of induction proofs that you'll be asked to complete during your HSC. So this video will be covering how to do each of the induction proofs as required by the NESA syllabus. So the first proof we're going to be looking at is our induction proofs, which is the first step is to prove true for the base case. This means to have some sort of like initial case that allows us to prove that our statement is true for at least one case. So an example would be we want to prove that the sum of all numbers 1 plus 2 plus 3 so on up to n is equal to n on 2 1 plus n. A base case for this would be to show that the sum of the first number, i.e. n is equal to 1, is true such that the left-hand side is equal to the right-hand side. And by substituting 1 in for the left-hand side and right-hand side separately, we could then equate them and say that it's true. We then assume true for an arbitrary number k, which simply means to substitute k for n. However, now we assume that it's true for k, and by using this assumption, we want to prove true for prove true for k plus 1. The reason that we prove true based on an assumption is that it basically tells us, okay, if our assumption is true, then whatever results from our assumption, if that is true, then that means whatever our assumption was an accurate assumption, and therefore then because it's true for any arbitrary number k and k plus 1, it's true for all values, and therefore our statement is true. So the first proof that we're going to be looking at is our arithmetic sequences. So prove by induction that the sum of all numbers is equal to n on 2 1 plus n. So for our first step, we need to prove true for base case. It doesn't say it in the question, however, our base case is going to be n is greater than or equal to 1. So we want to prove true for n is equal to 1. That means our left-hand side is simply going to be equal to 1. Our right-hand side, however, is going to be equal to 1 over 2, 1 plus 1, which is equal to a half times 2, which is 1. Which is equal to left-hand side. Therefore, it is true for the base case. Now, our second step is to assume true for n is equal to k, where k is greater than or equal to 1, i.e. 1 plus 2 plus k is equal to k over 2, 1 plus k. The reason I have this little star thing here is so that we could call back to it later on, because you'll see a key step of an arithmetic sequence induction proof is this recursive aspect of it. In order to prove a sort of sequence or series, we need to recursively call back to the previous statement that we assume to be true. Because we assume this to be true, this will form a sort of quote-unquote axiom for our future arguments. So now our third step is to prove true for n is equal to k plus 1. So we're going to write required to prove, and then we're going to substitute in k plus 1. So we have required to prove 1 plus 2 plus k plus 1 is equal to k plus 1 over 2. And then I'm just going to quickly do k plus 2 and just simplify everything. So our first step, we're going to take our left-hand side, and what we're going to do, we're going to take this here, and Using our second step assumption, we're going to say this is now equal to k on 2, 1 plus k plus 1, which is equal to k squared plus k plus 2k plus 2 all over 2, which is then equal to k plus 2, k plus 1 over 2, which is now equal to our right-hand side. Therefore, true by induction. So the key step here was to notice how we used this substitution here. So in this case, we were very lucky because when we substituted k plus 1, we immediately had the left-hand side from our assumption here. However, that will not always be the case, and sometimes we'll have to rearrange and solve for it. So if we move now into our geometric sequences, this will be almost the exact same process. So the first thing is we prove true for n is equal to 1. This is our base case here. So our left-hand side is going to be equal to, is equal to 2 to the 1, which is equal to 2. Our right-hand side is equal to 2 to the 1 plus 1 minus 2, which is equal to 4 minus 2, which is equal to 2, which is equal to the left-hand side. Therefore, it is true for n is equal to 1. Now, our second step is to assume true for k, i.e. 2 to the 1 plus 2 squared plus 2 to the n is equal to 2 to the k plus 2 to the k is equal to 2 to the k plus 1 minus 2. Now our third step is to prove true for n is equal to k plus 1. So now we're going to be required to prove 2 to the 1 plus 2 squared plus 2 to the k plus 2 to the k plus 1 is equal to 2 to the k plus 2 minus 2. So what we're going to do is we're going to rearrange our left-hand side now. So now that we have this here and we have our second assumed statement, what we're going to do, that's now equal to 2 to the k plus 1 minus 2 plus 2 to the k plus 1. So now what we're going to do is we're going to group our 2 to the k's plus 1 together. Now we get 1 plus 1 minus 2. And then that becomes 2 to the k plus 2 minus 2, which is equal to our right-hand side. Therefore, true by induction. So what you're going to notice is this is almost the exact same solution to our arithmetic sequence now. So we have our substitution here. We have our required to prove statement. And as soon as we substitute in, it's all about simplification. And it's the same thing with this geometric sequence here. We substitute it in here using our assumed statement. And then we just simply simplify down to get our right-hand side. So this is the general when you when you try to prove one of these arithmetic or geometric sequences by induction, this is going to be the process that you actually do this. However, when we move on to a bit more complex stuff like sums of factorials, the solution might be a little bit harder to find than our geometric and arithmetic sequences. So this is going to be how to solve our sums of factorials now. So this is from the 2025 HSC Extension 1 Math exam. So our first step is going to be prove true for n is equal to 1. Our left-hand side is going to be equal to 1 times 1 factorial, which is equal to 1. Our right-hand side is going to be equal to 1 plus 1 factorial minus 1, which is equal to 2 minus 1, which is equal to 1, which is equal to our left-hand side. Therefore, true for n is equal to for n is equal to 1. Now, our second step, assume true for n is equal to k, where k is greater than or equal to 1, i.e. 1 times 1 factorial plus 2 times 2 factorial plus k times k factorial is equal to n plus 1 factorial minus 1. Now, our third step is to prove true that n is equal to k plus 1. So now, if we quickly write this out, we're going to be required to prove 1 times 1 factorial plus 2 times 2 factorial plus n times n factorial plus n plus 1 times n plus 1 factorial is equal to 1 times 1 factorial plus 2 times 2 factorial plus k times k factorial plus k plus 1 times k plus 1 factorial is equal to k plus 2 factorial minus 1. So, our left-hand side, using our assumption, is going to now be equal to n plus 1 factorial minus 1, or k plus 1 factorial minus 1 plus k plus 1 factorial k plus 1. And then by taking out a factor of k plus 1 factorial, we get 1 plus k plus 1, which is equal to k plus 2 k plus 1 factorial minus 1. However, this is now just equal to k plus 2 factorial minus 1, which is equal to our right-hand side. Therefore, true by induction. So this might seem a little bit more complex, just because of the fact that it has a factorial. However, the only new addition to it now is the fact that we have a few more rules to play around with. So it's the same process of substitution, same 3 steps. However, now, in addition to just simple arithmetic, we now have the ability to group together factorials. So all that changes is how you approach it and how you're capable of considering how to actually modify your approach to account for this change. And it'll remain quite simple, and it won't really deviate too much from our geometrical arithmetic sequences. However, divisibility is where things begin to diverge. So, this is how to do a divisibility question for Extension 1 Math. So, our first step will be to prove true for our base case, which is n is equal to 1. So, instead of having a left-hand side, actually, what we're going to do instead is we're going to have just simply we're just simply going to substitute it in. So what we're going to say is now 2 to the 3, 1 plus 13 is equal to 8 plus 13, which is equal to 21, which is equal to 7 times 3. Therefore, true for n is equal to 1. Now, our second step is going to be to assume true for n is equal to k, where k is greater than or equal to 1. So now what we're going to do is we're going to develop some sort of expression here. So we have 2 to the 3k plus 13 is equal to 7p, where p is greater than or equal to 1, and p is some integer, is some positive integer. Now, step 3. Prove true for n is equal to k plus 1. Just before we continue, we're going to quickly mark this here. So we're going to be required to prove 2 to the 3 k plus 1 plus 13 is equal to 7q, where q is greater than or equal to 1, and q is a positive integer. So what we're going to do is we're going to say our left-hand side is equal to 2 to the 3 times 2 to the k plus 13. And now we're going to quickly do an aside right here and rearrange our star equation. So we have now 2 to the 3k is equal to 7p minus 13. And we're going to refer to this as just 1. Or that might be a bit confusing, so we're going to refer to it as beta. So now what we have is we're gonna we have this 2 to the k here, or 2 to the 3k, sorry, and we have this 2 to the 3k here. So we're gonna say using beta, that's gonna be equal to 2 to the 3 times 7p minus 13 plus 13. And now you might be able to see what's happening from here. We're going to take out a factor of 7 and we're going to go 2 to the 3p. So we're going to take out this here and simplify it into this in one step. And now we have these 13s here. So what we're going to do is in one step, we're going to take these out and group them together. So we have plus 13, we're going to have this 1 from here, minus, and now what we're going to do is we're going to take this 2 to the 3 here. So we're going to go 1 minus 8. That's now equal to 7, 8p plus 13 times minus 7. Now what we could do is we could go 7 and we could go 8p minus 13, which is equal to 7m, where m is some positive integer. And now we show that this expression holds true, where q is equal to 7m. For example, that's what we could say. We could say, instead of 7m, we could say, therefore, q is equal to 8p minus 13, therefore, and we have to conclude, therefore true by induction. So this is the way that we do a divisibility proof. So we have our assumption here, and then we substitute it in by rearranging it for whatever value we want. And then it's all about using the tools that we have so that we could simplify and factorize out some value or coefficient. So here we were trying to factorize out 7 to show that it's divisible by 7. However, we could do this for so many other problems. But today, that's everything we're going to be looking at when it comes to induction proofs. And I hope you have a great rest of your day.